My name is Alexander Biryukov, and this is Solidity 101 webinar. I'm a senior blockchain developer. I have participated in several real-world blockchain projects developed on mainnet, and I have also been a full-stack developer since 2014. So if you want to get some consulting or you want me to develop your project in Solidity, please feel free to contact me on LinkedIn or on Telegram. And for blockchain training services, you can also book me via coding bootcamps. Okay, I want to make this presentation more practical, so I want to just do this quick TLDR version. If you want to create your own ERC20 or NFT ERC721, you can do this with this Open Zeppelin wizard. No coding is required basically. In order to do this, you can just select the name of your token. For example, let's call it my ERC20, and let's make the symbol ME2. Let's make it mintable, then open in Remix. Remix is an IDE for Ethereum Solidity development. Let's refresh it because it's a little bit sluggish. Okay, it's compiling. Now it's done. Let's switch the tab. We can select our contract and try deployment to the simulated test network. It's successful, so we can now go ahead and try deployment to MetaMask. It's injected Web3. Okay, the MetaMask is asking us to confirm the transaction. Let's click confirm, and we can see the status here in the console. Okay, looks like it's done. Now we can see, oh no, it was not done because it was not connected. Okay, we can try it again. Okay, let's wait a little bit. Now it should be done. Right, we can see here contract deployment and can also see the result in the block explorer. Just like with a real network, it's just a test network is basically identical. It has the same tools, even block explorer and stuff like that. And we can also copy this contract address and add it to our MetaMask. It found the token. You can see our symbol and decimals. Let's import it. Okay, you can see the token is here. Now let's interact with it a little bit. Here, let's choose the second deployment to the test network. And here you can see these are functions for reading and these are for writing. So for example, we can see who is the owner of the contract. It should be my address that I used for deployment. Let's copy this address and let's mint some tokens to it. We'll need a lot of zeros because this contract has default 18 decimals. Now let's confirm the transaction in MetaMask. Wait for a second. Okay. It's still pending. Now it's done. Great. So here we go. We have 2 tokens and we can see them here even in MetaMask. Great. So we learned how to create our own ERC20 and deploy it to testnet. And basically the same can be for mainnet. We can just select the network which should be used for deployment here in MetaMask, for example. We can switch to Ethereum mainnet or Polygon mainnet or any other network. You can add your own network here. And also you can do the same thing for NFTs. This ERC 721 is the standard for NFTs. So we can just paste your picture URL here and also select the features, open in Remix, and all the steps that I did for ERC20 for your ERC 721. But I won't be doing this thing for now because I think you got the idea. Let's go back to theory. Okay, so you saw Solidity probably here a little bit. So the language is object-oriented, statically typed, curly bracket, influenced by C++, Python, and JavaScript. And Solidity compiles to EVM bytecode, and there are several EVM compatible networks other than the Ethereum mainnet. These include Binance Smart Chain, Polygon, Gnosis, Phantom, Celo, Avalanche C-Chain. Okay, so Solidity, just like many other languages, have value types and reference types. So the interesting value types here are address types, which are basically just uint 160, but they have some extra functionality around them. And the main difference between value types and reference types is that value types are passed by value and reference by reference, obviously. And therefore, reference types can be stored separately in some other locations, such as memory or storage. Or call data, for example, and only reference will be passed on stack. So here you can see 6 different locations where EVM can store its data. So EVM is stack based, and that's why it has stack, just like Java or C#, for example. It has a memory, which is also similar to those languages. Storage is basically blockchain itself. It can be thought of as a database because it has permanent storage location. And call data is basically arguments that you pass when you call a function. Code includes constants, so it can also have some data in it. And logs are basically the data that is passed with events. Okay, functions visibility. So in Solidity, functions can be private, which means they're only accessible to the contract itself. Internal, which means they are accessible by the contract itself and its descendants, the contracts that are derived from it. External visibility means that the function is not accessible in the contract itself. It can only be accessed via an external call. And public visibility means both internal and external. It means that function can be called both in the contract in its descendants and also via an external call from other contracts or even by an externally owned account, just like we did here in Remix, for example. Okay, contract creation. As we saw, we can create a contract externally by using Remix, for example, using an externally owned account. And also it's possible to create a contract internally, which means by instantiating a contract via a new keyword, like here in this example. And there's also a difference between two syntaxes. You can create a contract with salt, and this will use a separate opcode from the regular contract creation, and it's especially helpful for predicting the address where the contract will be deployed to, because with the regular contract creation without salt, the contract address will depend on the number of transactions that preceded it, which is kind of not so convenient because it's impossible to predict upfront how many transactions there will be from this contract. Okay, inheritance. Just like many other programming languages, Solidity has inheritance, and its inheritance is more similar to the one of Python and C++, because Solidity has multiple inheritance, which means that a contract can derive from two or more other contracts. And the potential conflicts that appear during this inheritance scheme are resolved using something called C3 linearization, which you can read more about in Wikipedia. And let's have a look at some code. Here, for example, contract is the base contract for contracts B and C. So we can see that these contracts B and C and derived from contract D. And as for the function, it has to be public, as we learned, or at least internal in order for it to be visible in its descendants. And also we'll need to use this virtual keyword in order for this function to be overridable. And we'll need to use this override keyword to override this base function. And if we still need to this function to be override to be overridden further, we should use this virtual keyword again. And we can see here that the contract A derives from both contracts B and C. And this function overrides these two, and this should be explicit in Solidity. Okay, what else? Libraries. Libraries are basically very similar to contracts, and the main differences are that libraries cannot have state variables, cannot inherit or be inherited, and cannot receive ether and cannot be destroyed. Okay, we still have some more time, so I'm going to show you some code examples and just discuss the code a little bit. Solidity has similar syntax for comments, similar to many other languages. This is pretty standard. And the second line is called SPDX license identifier, and it's a really good idea to use this license identifier. It's just a convention. Of course, it's possible to deploy contracts without it, but it's a really good idea to use it. This pragma solidity line tells the compiler on which version of Solidity we want to use. And this caret notation says that any version newer than 0.8.0 is good. If we want to specify the exact version, we should use this notation. And if we want to use any version between two specific versions, we can use this notation. Okay, so this is a simple storage contract which has this favorite number field, and this field and all the other fields, people and name to favorite number mapping are stored in storage, which means they will be permanently written to the blockchain. And this is just our struct type declaration. We can actually move this declaration outside of the contract and it will still compile. So it's not a field of this contract. Okay, so this is a dynamically sized array, which means that we can add as many items to it as we want. And this is a mapping. Mapping is similar to a dictionary, or basically it's an associative array, which means you can retrieve the value by its key. It's a key value store. And here is a function to save and to set a new value for our favorite number field. So the user of this contract can pass this argument, and it will be assigned to this field of our contract. So let's deploy this contract and see how it works. We can select this simple storage contract and let's deploy it to the simulated JavaScript VM to make it faster. Okay, here are our functions. So we can, for example, store some value to it, and now click retrieve and we can see the result. It says 42 because it was saved to this storage location. Okay, so this retrieve function has a view keyword, which means that this function cannot change the storage. It can only read from it. And it's also possible to use a pure keyword, but in that case, like pure, in that case, this function won't be able to read from storage as well. It can only use its input. It says a compile error because in this function we are trying to access this storage location. So let's make it view again. Okay, so our last function, add person, receives two values. It accepts two arguments, and then it creates a new person using these arguments. So we can use this syntax to create a new struct, and we say that it will be saved to memory because we don't need to save this person to storage because we don't have a dedicated space for just one person, and this object is just temporary. We can later use it, for example, in this line where we can store this previously created object to our storage array. And also at the same time, we are storing this this number and to our mapping by the key of name. So in the same function, we are saving this struct to our dynamic array, And we also store these two values in our mapping. So this value is associated with this key. So let's check how it works. We can add some person by, let's say, John, for example, and his favorite number will be 99. Okay, so now we can read we can read the value from this public array, for example, because this array is public, a reader function is generated for us automatically by Solidity, so we don't need to write this function like here, retrieve. This field was favorite number field was private because it doesn't say public, so it's private. And that's why we needed to write this separate retrieve function. But if we made this public, and the Solidity compiler would create a reader function for us. So that's what we have for people, for example. So we can just read the first index of this people array, and it says John, and his favorite number is 99. And also this mapping is public, so we can read from it as well. We can use the name John, and it says 99. And we actually can use some other keys, and for example Jack, and we'll see the default value in that case, which is 0. Okay, and the same can be actually done with the array, so we can just query some random number, but in that case we'll get an error because unlike the mapping, our array doesn't contain the default values. Like for every index, it knows how many elements were added to it. Okay, so this is pretty much it, I guess. Should you have any questions, I will be happy to answer.